Okay. In the last class, we started working with exponential functions. Those were things like y equals b to the x, where b is a constant and x was a variable. Or if you wanted to switch the roles of y and x, you could write that as b to the y equals x, right? So that the y and the x's are the variables and the b is a constant. And we saw last time in class that sometimes when you deal with exponential equations, you want to take the inverse of the exponential function. And so I said that's great motivation because for this next section, which is logarithmic functions, because logarithmic functions are exactly the inverses of exponential functions. That's their role. So let's just start with that definition. The inverse function of the exponential function with base b is the logarithmic function with base b. Okay, so here b is the base, here b is the base. Okay, and x and y are both variables. Okay, so what does it mean to be the inverse function again? Remember, that means that f of f inverse of x equals x, and f inverse of f of x equals x, right? These functions undo each other. So if I start with e to the x, right? If f of x is e to the x, then what's f inverse? F inverse is ln of x, the natural log of x. If I start with f of x is b to the x, then f inverse is by definition log base b of x. Okay? And we always have this property that because these are inverses, we're saying that log base b of b to the x must be equal to x. For any value of x, that has to be true. And also, b raised to the log base b of x also has to equal x. They're inverses of each other. Okay, so let's just keep that in mind. Whenever you see a log, you just need to think it's an inverse. It's undoing the exponential function. Okay? And now I claimed here that these two expressions are equivalent. B to the y equals x is equivalent to log base b of x equals y. Well, why is that? If you take this first expression, b to the y equals x, that first equation, and you evaluate log base b on it, what do you get? You get log base b of b to the y equals log base b of x. But remember, log base b is the inverse of b to the y. So you just end up with y equals log base b of the x. Okay? So whenever you see log base b of x equals y, you can think of that as b to the y equals x. Or if you see b to the y equals x, you can think of it as log base b of x equals y. Okay, so let's use this property. Let's write each equation in logarithmic or an exponential form. So we're starting with log base k of 64 equals 3. And the goal is to write this as an exponential. So what you would do is you would take k raised to the log base k of 64 equals k raised to the third. And now k to the log base k of 64 is just 64. So you get 64 equals k to the third. In the second equation, we have 2 equals log base 5 of x. So now, b is 5 in this case. We want to raise both sides of this equation to the fifth. Not to the fifth. You want to take 5 to both sides of this equation. So it's 5 squared equals 5 raised to the log base 5 of x. Okay. I mean, essentially what we're doing is we're starting with an equation, a equals b, right? And we're evaluating a function f on both sides. So you should get f of a equals f of b. That's what we're doing here. We're f, in this case, is 5 to the x. Okay? So we're sticking the equation into the 5 to the x. And it's just a standard fact that if a equals b, then f of a is going to equal f of b. So sorry, that was just a little aside. So we start with 2 equals log base 5 of x, and we can evaluate both sides of the equation by the function 5 to the x, and we get 5 squared equals 5 raised to the log base 5 of x. But 5 to the x and log base 5 of x are inverses of each other. So this right-hand side here is x. So we get x equals 5 squared. Okay, now if you give me an exponential equation like 3 to the m equals 1 over 27, then I can write that as a logarithmic function by taking log of both sides. And in this case, I'm going to take log base 3, because here I have an exponential function or expression with a base 3. So I'm going to take log base 3 of 3 to the m equals log base 3 of 1 over 27. So then I would get something like m equals log base 3 of 1 over 27. Or if you wanted to simplify this further, you could write this as log base 3 of 3 to the minus 3, because 27 is 3 cubed, and 1 over 27 would be 27 to the negative 1, so you get 3 to the negative 3. And then because I'm taking log base 3 of 3 to the something, right, I'm just going to be left with that something. So here I'm getting that m equals negative 3, because log base 3 and 3 to the x are inverse of each other. So this is like log base 3 of 3 to the x, where x is negative 3. So it just cancels. Okay? Okay. So this next equation is 64 to the 1/3 equals 4. The cubed root of 64 equals 4. And here I'm going to take log base 4. Let's see, this is 64. Let me write it like this. This is 64 to the 1/3 equals 4. And if you're looking at this as b to the y equals x, then we want to write this as log base b. Well, b is 64 in this case. So log base 64 equals log base 64 of 1/3 equals 4. It's the way to rewrite this as an equation, a logarithmic equation. Okay, now we want to look at some basic properties of logarithms. So the first one just says that log base b of b equals something. Well, this is asking b to what equals b? And the answer is 1, right? B to the first power is equal to b. This next equation is asking b to the what equals 1. I think you guys all know that anything to the 0th power is equal to 1, so log base b of 1 should equal 0. And then these last two equations are just reminding us that these are inverses of each other, so that if you have log base b of b to the x, that should be equal to x. The log base b is the inverse of the b to the x function. And b raised to the log base b of x should also be equal to x, because these things are inverses of each other. This is like just saying f inverse of f of x equals x, and here we're saying that f of f inverse of x equals x. Okay, now we can use these to do the next example, which is just to evaluate these expressions. So we already saw that log base b of b is equal to 1, so log base 11 of 11 has to equal 1. This is just saying 11 to the first power is equal to 11 to the first power. The next equation, log base 6 of 1, that has to be equal to 0, because we're asking 6 to the 0th power is equal to 1. The next one is log base 4 of 4 to the 6th. You should be able to see that's 6. And the very last one, log base 3 of 27. Well, that's log base 3 of 3 cubed. So log base 3 of 3 cubed is 3. Alright, now, as I've said many times already, logarithms are inverses of exponentials. And so if your exponential function looks like this, then because the log is the inverse of that function, it should be the mirror image across the line y equals x, right? And so that means that it's going to look like that red graph right there. And notice that With exponential functions, your range is from 0 to infinity, and you have a horizontal asymptote at y equals 0. So when you flip that across the line y equals x, you now have a range of 0 to infinity, and you have a vertical asymptote at x equals 0. And you can see that if your exponential function looks like this, because your b is between 0 and 1, okay, which we saw last time, it would look something like that. Then its mirror image across that line y equals x looks like the red curve here. Oops. That red curve right there. And so since you already saw that any exponential function goes through 0, 1, any logarithmic function should go through 1, 0. Because if b to the 0 equals 1, then log base b of 1 has to equal 0. Alright, and now this is very important. We've looked at domains of rational functions and domains of radical type functions, and we saw that basically the only ways that things can go wrong in this course so far have been if you divide by 0 by a rational function, you don't want the denominator to be 0, and if you're taking the square root of something, you don't want to take the square root of a negative number. Now for logarithms, the only thing we don't want to do is take the log of a 0 or a negative number. So that's what this statement is saying right here. The domain of log base b of g of x is wherever g of x is greater than 0, strictly greater than 0. We can't take log base b of 0 because there's nothing that you can raise to, there's no power that you can raise a constant to and get 0. Okay? So let me just write that down as a kind of a mantra. You should just remember this sentence, that you cannot take log base b of a negative number. Or 0. Okay, just remember that, and you'll always be able to figure out what the domain of the function is. So in the first case, we have log base 10 of x minus 10. And if ever if ever you see log and you don't see a base in this class, it means because it's log base 10, and it happens so frequently we just write log. And on your calculator, you'll see a log button. That's always the log base 10 button. Okay. Now what we're asked is, what's the domain of this function? Well, again, this is wherever, in this case, g of x is x minus 10, right? Where it's wherever g of x is greater than 0 would be the domain. So we want to find when g of x equals x minus 10 is greater than 0. Oops. And that is when x is greater than 10. So the domain is all real numbers greater than 10. You could write that in interval notation like this, or you could just say the set of all x such that x is greater than 10. Or you could write out in words, or you could do a number line. Okay. Now in the second example, we have f of x is log of x squared plus 3x minus 4. And again, we're looking for where this is g of x. Let's say we're looking for where g of x is greater than 0. And so let's see here. To find the domain, we find when x squared plus 3x minus 4 is greater than 0. And the easiest way to do that is just like pretend like you're setting this equal to 0 and solve, and then check points in between. So if you want to do that, you would probably factor this as x minus 4, no, x plus 4, and x minus 1. Okay? And then I would plot those points on a number line. Okay? And okay, if you do some analysis we did in the last chapter, and you look at the leading coefficient, which is 1, it's positive, and the fact that this is an x squared, we know that this function is going to be cupping up, and it's going to pass through the x-axis at x equals -4 and x equals 1. Those are the two zeros here, right? So this is for this to equal 0, you would have x equals -4 or x equals 1, or the zeros of x squared plus 3x minus 4. And so that tells us that this is going to be greater than 0 over here and over there. Okay, so that tells us that our domain is all real numbers to the left of -4, so -infinity to -4, union 1 to infinity, because that's where x squared plus 3x minus 4 is strictly greater than 0. Alright, the last little bit here in this section, we want to look at common logarithms. Logarithms that show up a lot. So logs with base 10 are just written as log, and logs with base e are written as natural log, or ln. Okay. These are common, and like I said, so this is the log button on your calculator. And if you want to log base e, you're gonna hit the natural log button on your calculator. And those are the only two logs you can really evaluate with your calculator, unless you know this very important property. Then that's called the change of base property. And the change of base property, all it says is that log base a of b is equal to log base b over log base a. And then where this is log base 10, right? This is log base b over log base a, or it's also equal to natural log of b over natural log of a. So it's a way of changing bases. And so if you use this property, you can plug any of these expressions into your calculator. Because if you need to evaluate log base a of b, you just write as log base 10 of b over log base 10 of a, or ln of b over ln of a. So this is very important if you want to be able to use your calculator. Okay, so now let's just evaluate some of these. It says evaluate log, or natural log of e. That's like natural log of e to the 1, right? So that is just going to be 1. If you see log of 10 to the 8th, that means that you're doing log base 10 of 10 to the 8th, which will give you 8. And finally, if you see natural log of e to the 13x, that's going to be 13x. Okay, so that's all from section 4.2. Now we're going to move on to section 4.3. Remember, we voted on this in the last class, and you guys decided you wanted to cover 2 sections on Tuesday of this week. So, sorry, let me cancel that out. This is Tuesday, not Thursday. We're covering 2 sections so that you guys can take your Chapter 4 test on November 16th. So, Chapter 4 test is Thursday, November 16th, and that's so that you don't have to have any class on the Tuesday before Thanksgiving. So there's no class on Tuesday, November 21st. And remember, we all voted on this one class on last Tuesday or Thursday, and this is what we came to a consensus of, like kind of a unanimous consensus actually, that you would prefer to take the test on Thursday, November 16th, so that you don't have to worry about it on the Tuesday before Thanksgiving. Okay, now in section 4.3, we're going to work a little bit more with logarithms, and we're going to work with some common properties. And so the first one says that log base b of m times n is log base b of m plus log base b of n, and that's called the product rule. And I claim that it's coming from the fact that if you take b to the m times n, that's the same as, sorry, if you take b to the m times b to the n, that's the same as b to the m plus n. Okay, the next rule is log base b of m over n, which is log base b of m minus log base b of n. The quotient rule is coming from the fact that b to the m over b to the n equals b to the m minus n. So these rules are coming from the exponential rules, and I might prove that to you a little bit later. And the last one says that if you take log base b of m to the p, that's the same as p times log base b of m. So you can take the power, or the exponent, out in front. And that's called the power rule. And again, I claim that this is coming from the rule that b to the m raised to the p is equal to b to the m times p. And rather than take time out in this right now to prove these to you, maybe I'll post some Khan Academy videos that give you these proofs. They all follow from these rules over here, and then if you write them in terms of logarithms and just follow your nose, you'll see that they're true. And you might be wondering why the heck you would care about these. Well, these rules allow you to expand or condense logarithmic expressions, and in calculus that's really important, because you're going to want to have to take derivatives of logarithmic and exponential expressions because they show up all over the place in nature, and typically taking the derivative of a product of stuff or quotient of stuff or something raised to a power is tricky, but if you expand them out using these logarithm rules, then you can take the derivative of each part separately and add them up, and that's just much cleaner. So all I'm saying there is that you should keep this handout if you're taking calculus. Because these rules come in really handy in your calculus classes. And so I suspect that that's why this section's in the book is just for the students going on to calculus. It doesn't mean you shouldn't know it otherwise, because again, exponentials and logs show up everywhere, especially when it comes to financial problems and figuring out your student debt. So you should still know these rules, but these expansion rules are really important for calculus. Okay, so here we're asked to expand the following expression and evaluate when possible of log base 9 of 9x. So here we're going to use the product rule because we have a product inside of the logarithm. And so you can write that as log base 9 of 9 plus log base 9 of x. Because if you have a log of a product, you can write it as the sum of the logs. And now log base 9 of 9 is just 1. So you get 1 plus log base 9 of x, and that's about as simplified as you can make it. In part B, we have a quotient rule. Right? We have a quotient rule, so we're going to use this part right here, that rule right there. And so we're going to write this as log base 5 of w minus log base 5 of 25. And maybe I'll write that second expression as log base 5 of 5 squared. 25 is 5 squared, right? And then we can use the power rule. So let me just say that this was quotient rule here. And then this will be power rule, which you should always do at the end if you're doing expansions. So now this will be log base 5 of w minus, and now this, the power rule says we can bring that exponent out front. So this is 2 log base 5 of 5. But log base 5 of 5 is just 1, right? So we end up with log base 5 of w minus 2, because this log base 5 of 5 is just 1. Okay, here's an even uglier expression. It's log base a of the square root of 2 times t to the 6th. So I'm going to start with product rule again. Product rule says that we should write this as log base a of the square root of 2 plus log base a of t to the 6th. And now we'll use power rule in just one second. Let me write this as 2 to the 1/2. So log base a of 2 to the 1/2. I'm just replacing square root of 2 with 2 to the 1/2 there. And then plus log base a of 2 to the 6th. And now we're going to use the power rule here. So power rule says that this is all equal to 1/2 log base a of 2 plus 6 log base a of t. And again, that's about as far as you can simplify it. Okay. Here's one more. This one's even uglier because we have a product and a quotient rule. So I'll start with the product and quotient rule. I'm going to do it in one step just because I don't think it's that difficult to see. This is log base 10, or log of x to the 4th, plus log of the square root of x squared plus 3 minus the log of x plus 3 to the 5th. Okay? So where there was a quotient, I subtracted, and where there was a product, I added. And now we can use power rule, but let me just do one more step to make it a little bit prettier here. So this is log of x to the 4th plus log of x squared plus 3 all raised to the 1/2 minus log of x plus 3 to the 5th. Now I'm going to use power rule. So I'm going to bring those powers out front. Okay, so that's 4 times log of x plus 1/2 log of x squared plus 3 minus 5 log of x plus 3. Alright, now we're going to start with a sum of logs and then condense them into a product or a log of a product. So here we expanded using these power rules. We expanded. We started with like a log of just one product or quotient, or a product and a quotient, and then expanded out as a sum. Now we're going to take a sum and condense it into a product. Again, this is a technique that's helpful in calculus, which is then helpful in engineering and chemistry and everything else, physics, etc. So now we're going to condense, and it says that when you're condensing, you should always use the power rule first. So when condensing, always take whatever's out in front of the logs and move them up. Okay, that's going to be your power rule. Do that first if you're condensing. So in power rule, we want to write this as ln of x to the 4th plus ln of y to the 7th minus ln of z cubed. Let me just put that there. Okay, and now we're going to use product and quotient rule. So using the product and quotient rule, we get that this is natural log of x to the 4th times y to the 7th over z cubed. So where there was a minus sign, we divided, and where there was an addition sign, we multiplied the stuff inside the logs. And that's the final answer right there. Okay, now here we have 5 ln of a minus 1/3 ln of c plus 2. So again, we're expanding, so we always want to, or we're condensing, sorry, so we always want to use power rule first. And so now you got ln of a to the 5th power minus ln of c plus 2 to the 1/3. Okay, and so then we can use quotient rule. And so that is ln of a to the 5th divided by c plus 2 to the 1/3. Or you could write that as ln of a to the 5th over the cubed root of c plus 2, if you wanted. Either one of these is right. Okay. Now, let's see here. So now we have 1/4 2 to the ln of x minus 4 minus ln of x minus 3 ln of x squared plus 9. And so there's a couple different ways we could start, but if we wanted to use power rule, you could either bring up like this 2n as an exponent and that 3n as an exponent, or I'm going to just do one step before that, and I'm going to distribute the 1/4. So I'm going to distribute this. Either way, this would work out just fine. But if you distribute the 1/4, then 2 times 1/4 is 1/2 ln of x minus 3 minus 1/4 ln of x minus 3/4 ln of x squared plus 9. And then you could do the power rule. So this is ln of x minus 3 to the 1/2 minus ln of x to the 1/4 minus ln of x squared plus 9 to the 3/4. And then you could use quotient rule to write this as the natural log, or ln of x minus 3 to the 1/2 over x to the 1/4 times x squared plus 9 to the 3/4. And some people will probably ask, why did I multiply the things on the bottom? And that's because it's like I started with x minus 3 to the 1/2. I'd be dividing by x to the 1/4, and then dividing by x squared plus 9 to the 3/4. And so that'd be the same as like multiplying, let me just say this, that if you have a over b over c, that's the same as a over b times 1 over c, or a over b times c. That's why I multiplied on the bottom there. Okay, so that was one way to do this problem. I said that you could do it a different way, and the different way would be don't distribute right away. Okay, so if you don't distribute right away, then you have this 1/4 hanging around for a long time. But you could write this as ln of x minus 3 squared minus ln of x minus ln of x squared plus 9 cubed. And then you could leave that 1/4 there still and do ln of x minus 3 squared and then divided by x divided by x squared plus 9 cubed. And now, because you have this 1/4 out front, you could bring that in as a power of this whole thing, right? So this becomes, by power rule, this becomes ln of x minus 3 squared over x times x squared plus 9 cubed, all raised to the 1/4 power. And you might say like, oh, that's different than what we got over here in green. But if you look at those, they're actually the same thing, because x minus 3 squared raised to the 1/4 is the same as x minus 3 to the 1/2, right? And on the bottom here you have x to the 1/4. Well, that's just, basically all we did here was we pulled this 1/4 out. So it is actually exactly the same thing. Okay. Okay, so I touched on this before. I think I got ahead of myself, but it's the change of base property, and so I'm going to write it just slightly different this time. I'm going to write it as log base m of n is log base b of n over log base b of m for any choice of b. So the choices we typically use are log base 10 or log base e, which would be natural log. And again, this is really important if you're using a calculator, one of these scientific calculators. So as an example, if you need to evaluate log base 30 of 4, then you could write that as log base 4 over log base 30. And then in your calculator, let's see, what would you type in? So if you're plugging that into your calculator, I would write it as the 4 button, the log button, divided button, 30 button, log button, and then equals. And you should get roughly 0.408. Okay. And you could have also written this as natural log of 4 over natural log of 30. So you can either use the log button, or you could also use it as natural log button. So this is equal also to natural log of 4 over natural log of 30. Okay, so that's just a little aside. If you need to use your calculator to evaluate these things, you really only have 2 buttons that can evaluate logs, but using the change of base property, you can evaluate any log you want. Okay, and that's all we have for today. I'll see you in class on Tuesday.